Starting in the great name of Allah, the Merciful, the Beneficent. Assalamu alaikum. I am Muhammad Adil with my groupmate Hasnain Ali, and today we are going to present our final year project that is fabrication of soft and comfortable pressure sensing shoe sole for intuitive monitoring of human quality gaits, which is done under the worthy supervision of Dr. Afaq Manzoor Sumro and co-supervision of Dr. Muhammad Waqas Sumro. So you must be wondering, what does gait mean? It simply means how a person walks. So without uh, without delaying anything, let's discuss today's agenda, that is introduction of the project, the literature we have surveyed, problem statement, aims and objectives, fabrication and integration process of pressure sensors, testing of the pressure sensors, integrating those pressure sensors in shoe soles, a dedicated graphical user interface, and a demo with some references. So, introduction, the study of how a person walks or runs generates great insights of pain in feet, diabetic feet, imbalanced walk, monitoring health, evaluating techniques in athletes, the progression or regression of diseases in the human body. The human gait monitoring plays a significant role to understand such insights. It is a systematic examination of the way in which a person walks. So basically, it is conducted either for clinical purposes or for research purposes. In the clinical area, it is used for diagnosis, assessment, or monitoring the results of the treatment, while research covers a wide range of disciplines, including clinical medicine, biomechanics, physiology, and human performance. There are many reasons why gait cycle analysis is important in both clinical and research environments, which are injury prevention, post-treatment confirmation, sport performance, evaluating effects of different conditions on the human body or feet. So this is basically the gait cycle or the gait phases. Uh, Acceleration, basically when a person walks, it starts with heel strike. Usually it represents the starting of a gait cycle. Then it is the foot flat, mid distance, push off, acceleration, mid swing, and deceleration. So basically this represents the normal human gait cycle or the gait phases in which a person walks. To truly understand such phases or gait cycles, it is important to understand or develop some tool to analyze gait cycle. Therefore, we have some problem statement, that is human gait depends on a complex interplay of major parts of the nervous, musculoskeletal, and cardiorespiratory systems. To truly understand such systems, pathologies, and injuries in human locomotion, we must first understand the methods in which a person needs to move, that is, uh, the gait cycle. Gait disorder leads to a loss of personal freedom, falls and injuries, and result in a marked reduction in the quality of life. That is why we have aims and objectives of our project, which are to fabricate pressure sensor for intuitive monitoring of human quality gaits, to embed those pressure sensors in soft and comfortable shoe soles, and to develop user-friendly graphical user interface GUI for monitoring purposes, and to apply the proposed smart shoe sole for rehabilitation of patients. And also our project covers two sustainable goals by United Nations, which are goal number 3, that is good health and well-being. It ensures healthy lives and promote well-being for all at all ages. And goal number 8, that is it promote decent work and economic growth, because we have used our own fabricated pressure sensor for these purposes. So why pressure sensors? We have several latest literature published in renowned journals, that is Nature, Springer Science, IEEE Axis for fabricating pressure sensor and gather the technical data. We found that there were different methods proposed for fabricating pressure sensors, which were piezoresistive, piezoelectric, or capacitive. So we decided to go for piezoresistive because it was very cost effective and it was very easy to use, or which was easy to make. While each type of pressure sensor holds its unique advantages and challenges, The choice of piezoresistive pressure sensors for our project, enhanced with EcoFlex and graphene composites, emerges as particularly suitable for intuitive gate monitoring. These sensors exhibit high sensitivity, conformability, flexibility, and real-time monitoring capabilities, which are the need of our project. So this whole picture uh, discusses methodology, how we are going to fabricate and integrate those pressure sensors in the smart shoe. Basically, it starts from very beginning, that is measuring graphene powder and mixing it with Ecoflex part A and part B with 1:1. And then we have our prepared or fabricated graphene and Ecoflex thin film. And then we have our pressure sensor layers, and then we have fabricated pressure sensor with us, and those that prepared or fabricated pressure sensor is then integrated into the smart shoe sole, or and then shoe sole is integrated in shoe for the human quality gate purposes. So fabricating thin film of EcoFlex and graphene by homogenization. So as you can see, we have used EcoFlex. It comes commercially. It comes with two parts. That is part A and part B, and we mix these both parts by 1:1, and we have used graphene uh, to mix and to prepare thin film layer. So homogenization of EcoFlex part A and part B by 1:1 with 5 milligram of graphene nano powder, resulting in 15 by 15 millimeter square thin film of EcoFlex and graphene composites with a thickness of 1.25 millimeter. As you can see, the process is very simple and easy to fabricate our piezoresistive pressure sensor. Moving towards fabricating a pressure sensor after the curing process of EcoFlex and graphene thin layer. Very first, the electrodes are positioned strategically within the sensor to enable accurate pressure sensing and piezoresistive measurements. Second, soft wire are soldered onto the electrodes, as you can see in the picture number 2. And the third, the thin film of EcoFlex is placed onto the electrodes to prepare the pressure sensor. So this figure uh, tells the layers of our fabricated pressure sensor, which are at the top. It is the adhesive layer, and then we have upper electrode, and then we have EcoFlex and graphene layer, then bottom electrode, and then adhesive layer, and then we have pressure sensor, our fabricated pressure sensor. So testing the fabricated pressure sensor, it is very easy to determine how pressure sensor works. It is to connect a multimeter in resistor measurement mode. The prepared pressure sensor exhibit negative piezoresistive behavior, meaning where its electrical resistance changes in response to applied pressure, meaning when we apply the pressure, the resistance of the pressure decreases. When we are not applying pressure, we have open circuit, and when we are applying very minimum pressure, according to the measurement, we applied 200 kilopascal, which showed 150 kilo ohm resistance, and then we applied maximum pressure, which was 750 kilopascal. It showed 200 ohm resistance. As you can see in the video, the resistance of the pressure sensor is changing when we are applying the pressure. Moving toward the testing the response of the fabricated pressure sensor, my groupmate Hasnain Ali will come over and explain further the results of the pressure sensor.
So after the calibration process, I mean to say after the fabrication process, we move towards the calibration process. So we came to know that the sensor is negative piezo resistive behaving. So we tested it with a weight scale, and we came to know that at no weight its resistance is highest, and at the weight of about 40 kg to 50 kg, it is get gradually decreases. Then at no weight, then after putting more weight on it, it becomes appro- approximately 8 or nearly approaching to 0. And this is the response regarding the time and pressure, that as much as the with the time we increase the pressure, so the graph will gradually increases. And then we have used this conversion of weight into Pascal formula, and we have made this table corresponding to the different weights, and we have used this formula. The pressure is equal to force per unit area, and in the area we have used the 15 into 15 square, which is the same area of our sensor. And uh, weight has been determined from the weight scale, and the g is the value of 9.8 meter per second square. So we have followed this table and we have been implemented in our calibration process. So this is the pressure sensor's response curve. This pressure in kilopascal and resistance, as much as the pressure is increased, the resistance will gradually decreases. So this shows the negative piezoresistive behavior of our sensor. And not only this, we have also compared with our sensor with the commercially available force sensing resistor, and we can see that its response is similar to it. But if we compare more, we can say that the FSRs is highly sensitive and it resistance is hard to control. So our sensors behavior is like we can control it, and we can somehow easily measure its response. So this is the comparison, which is almost similar. So furthermore, these are the characterizations of our pressure sensors. This is the active size area, thickness, resistance change, and the pressure range. And also we have the power supply less than 1 milliampere. It depends also upon the fixed resistor. And the sensitivity we have obtained is 0.02 Pascal per ohm. And this is the response time, recovery time 120 millisecond and 100 millisecond. And the hysteresis is 6%, threshold plus minus 10%, and cyclic response is 50 times. So after fabricating, we have integrated in the shoe sole, and we have used 5 pressure sensors, and their area, each one the area is 15 into 15 square. And these are the positions which where we have placed sensor 1 at toe, then 2 3 4 in the mid, and the sensor 5 at the heel. So we have tested it resistance before applying the pressure, and after applying the pressure it is showing variation and resistance in the DMM, digital multimeter. Then after that we embedded it with a smart box, and uh, we have used ESP32 for Bluetooth connection, and with wirelessly connecting it with our graphical user interface dedicated. So this is the summary, and this is the data acquisition block diagram, that we can embed as much as sensors. Then the data will be sent to ESP32. Then the conversion will occur in IDE, and then output will be shown in the GUI. So this is the pressure stride monitor graphical user interface, which is dedicated. Before applying the pressure, there are no values, and after applying the pressure there are color variations, and as well as the pressure on toe, pressure on midfoot, and pressure on heel values, and as well as their signals. So this is the demonstration of our project. Here, getting started, and the switch will be on. After that, we will connect to ESP32 or Bluetooth, turning on pressure stride monitoring. After a few seconds, it will start. So after applying pressure on the different regions of the foot, it will start and will be showing the pressure sensor signals, colors, and as well as the values. This comes under the walking demonstration. So this is the poster of our final year project. It covers whatever we have done and how we have fabricated it and how the results have been shown and how the results in GUI have been brought forth. So this is the conclusion and the summary of our final year project. Thank you so much.